joining. All right. I think we have just admitted in all those who were in the meeting room, waiting room. So some of them are connecting to the audio. So the rest, just seek your patience to hold on for a while. Just to introduce myself, my name is Casey Wong. I work for INTERTANKO. I'm based in Singapore, in this INTERTANKO Singapore office. With me are also colleagues who are in the INTERTANKO London office who's running the webinar today. So you will see some of them. We will have the speakers with the video on. And for the rest who are in the audience, you might get better sound quality if you can switch off your video. Yeah. So and also to mute yourself. In general, we will not have questions directed via voice, but we'll be using the Slido system. So maybe John or Jockey, can I trouble you to put on the Slido slide for the audience to maybe have the information on how to log on to Slido. You can do so via your mobile phone or separate mobile devices, or opening up another window on your laptop or computer to use the Slido platform. And there's actually a live active poll going on at the moment. There are 4 questions. Just we want to do a test of the views and opinions of everyone just before we start the webinar. Yeah, thank you. Just hold on for a while. We will commence probably in another 1 or 2 minutes. Okay, I think it's about time now. So, I'd like to welcome everyone again. So in the interest of time, we will commence with the webinar. So as I mentioned, the Slido platform will continue to run as we view the presentations. So just to introduce myself again, I'm Casey Wong, working for INTERTANKO based in Singapore. With me, some of my colleagues are John, Chaplin, and also Jockey Maya, INTERTANKO Secretariat, who was also helping to run this webinar. So without further ado, let me just give a short intro. So I think this webinar is quite key and timely, given that the MEPC 80 has just finalized the IMO 2023 GHG strategy. And so with the MEPC finalization, the objectives and outcomes and targets are very clear. But the issue now is the roadmap and the pathways to reach those targets are still not so well defined. So ships have to reach net zero by 2050, and with intermediate checkpoint targets of 30% in 2030 and up to 70% in 2040. And also there is a target set for uptake of zero or near zero GHG emission technologies. to represent at least 5% of the energy used by international shipping by 2030. So taking a leap into an investment decision for alternative fuel at the moment seems a bit uncertain for many ship operators, given there's the certification framework of well-to-wake or marine fuel is still under development. But what is clear that I think we cannot stand still, and also it's clear that although new building to use alternative fuel play a big role to reach the 2050 targets, but improving the fuel efficiency of the current fleet also continue to play a big part, especially in meeting the 2030 and 2040 targets, and especially in meeting the requirements under CII. So wind power is definitely one of the options, some of the actions that can be done now. So we look forward to hearing more from the various speakers today. So we will have Mr. Gavin Allwright, who will be setting the scene with his first presentation, followed by one of the technology providers, Rise Maritime, Mr. Frederick Gerhardt from Rise Maritime. And of course, we have two ship owners and operators who have actually made plans and in fact implemented plans. So Mr. Eric Hopland of Oshfeld and Mr. Chen Xiangjun of AMCL, who has already, these are the some of the more concrete plans that there's already some in the water, some in the building. And so we will have a Q&A at the end, and this Q&A will welcome audiences to populate them. So I think before we start with the first presentation, we can actually maybe have a look at the poll questions, poll chart, just to have a glimpse of where we are and the 4 questions. Maybe I can trouble John. Yeah. So scale to 1 to 10, how effective? So we are seeing 21% on the confidence chart. Okay. I guess this poll will still continue to run. I think you can still change your responses along the way. Maybe at the end of the webinar, we have time. We can come back and see what's the look of it. So next chart, please, John. Economically viable or not? Okay. So we have these are the distribution of responses. Seems quite positive. Okay, next chart, please, John. And of course, biggest barrier will be investment costs and of course operational concerns, which is why we have some of our speakers. I think we hope to hear more from them to cast more light on that. So next chart, please. And whether recommended or not, I think okay, in general, undecided, but there are some weightage towards likely and highly likely. So, okay, without further ado, Gavin, would you be ready to start?
Okay, can you hear me, Casey?
Yes, I can hear you. I hope the rest of the audience can hear you as well. If not, I think they can sound out on the chat box. Yeah, thanks.
Fantastic. Thank you very much. And some interesting survey questions and answers there. I'm actually going to link those maybe with a couple of the slides later in my presentation. So I've got about 10 minutes just to very quickly put the whole development of wind propulsion in perspective. So just very quickly, I'm the Secretary General of the International Windship Association, and our network now covers, I think we're actually around 200 active members now, but at the beginning of the year it was around 150 across from ship owners, shipbuilders, we have R&D centers, we have, of course, about 40 plus technology developers and project developers in wind propulsion too. And as you'll see, a lot of that activity is clustered in Europe. We have a very active hub in France. We've just announced a hub in the Pacific as well, based on the Marshall Islands. And we've got developments also in North America and in Asia. Very quickly, what does wind power deliver? What are we actually talking about here? Well, as an energy source, we're talking about zero emissions. That means, obviously wind, you don't need to mine it, refine it, transport it, store it, bunker it. It's zero emissions delivered to the point of use on the vessel at a zero cost for the lifetime, not just of the vessel, but of the system itself. Now, of course, the wind propulsion technology itself is not free. There are costs involved there. But I've put a few zeros here, zero development time. Well, what that really means is we have 13 companies with their systems in the market now. Some of them are more developed with 5 to 10 installations.
Jag ska sätta på högtalaren istället.
Others are less developed. Zero compatibility issues. What this really means is you can select any other energy source, any other fuel. There is no compatibility issue with wind. You can have wind plus ammonia, wind plus hydrogen, wind plus HFO, all of that. We're also talking about highly automated systems. The vast majority of the systems in the market, you don't need additional crew. These are automated and will be operated from the bridge. And zero capex with a question mark. I saw one of the issues around was the initial investment cost. Well, you could be looking at leasing or other types of sharing of the fuel savings that you get to actually pay for the system. So we could be moving to far less upfront financial burden and actually paying for these through the OPEX. And please do remember that wind propulsion is pretty much the only propulsion system that will pay for itself because it's using a zero cost energy source. Now, for retrofits, we're looking at between 5 to 20% of the propulsive energy for the ship, potentially optimized up to 30%. But please remember, this is on a motor vessel operational profile. So you're not making any changes for the ship to increase the wind propulsion, like speed or wind routing, etc. Now, if you move to an optimized new build, then of course you're integrating those systems onto the ship and into the ship's systems at the very beginning. So we're looking at the potential for primary wind vessels, 50%, anything up to 80% plus. We even have one member that's looking at a climate positive tanker, which I'll mention a little bit later, which generates more fuel than it uses. So, and that's possible with operational changes. Of course, windier routes, you're going to get much better performance than slightly less windy routes. Now, there are actually 7 technology clusters, and I could probably spend the rest of this webinar just talking about those, but I'll just touch on them very briefly here. Obviously, we have soft sail and dyno rigs. These are the wind systems that most people are familiar with. But we have hard sail or rigid sails, which if you're a yacht racing fan, then you've seen these systems on those vessels. Those are now being upgraded, and we're going to hear, I think, from Simon later about systems, and also from a couple of Chinese tankers with rigid sail systems on them. Then there are the Flettner rotors or rotor sails. These are rotating cylinders, and when the wind hits those, the rotation generates thrust through the Magnus effect, which is basically a difference in pressure on each side of the cylinder, which sucks the ship forward. And indeed, that is the way that most sails actually work, which enables you to go faster than the wind. Kites. Probably, if you're around my age, you probably saw the first generation of kites about 10 years ago. These are being redesigned, brought back into the market now. And then we have a thing called a suction wing or a suction sail, which is a rigid sail, but with a suction device inside, which sucks in the boundary layer around the stubby wing. and enhances the lift or the thrust. And then we have hull forms where the actual hull is being designed as a giant wing itself, which is very exciting development there, and turbines, which can be generating electricity, of course, but also can be delivering some thrust as well. Now, our approach, and we're going to hear a little bit more from other speakers about this as well, is we look at the whole energy system in this type of pie chart, where we have 4 segments, each around sort of 20%, wind delivering 20% across the fleet, looking at the activity of the vessel, the operational changes, optimization of voyages, etc. Then the vessel itself, optimizing the vessel, so air lubrication, integrating the EMS, etc., etc. Each of those segments could be delivering up to 20% or more, potentially more. And then filling the 4th segment with the eco-fuels that we hear so much about. And then a 5th segment, which could be any one of those combinations. But moving away from a fuel-centric approach, looking at it very much from an energy-centric approach. Now, wind propulsion market developments. Actually, this is a Maersk tanker that was outfitted in 2018 with a couple of Flettner rotors. What we're looking at currently, we have between, I think it's now 31 installations of vessels. And as you'll see, the largest segments are ro-ro, bulk carrier, and general cargo. There are 3 tankers in operation, but if we add wind-ready vessels, actually 6 chemical tankers were delivered this year, designated as wind-ready for capital ship management in Greece. And this is a growing trend, which I'll maybe touch on at the end. Now, looking out to the end of this year, or the end of this year, probably the end of Q1 in 2024, we're looking at around between 49 to 53 installations, and the 65 is in brackets is the wind-ready aspect as well. So we started the year at 23. We will be doubling that this year, but actually there were 8 installations of wind propulsion last year. There are 24 plus this year. So we could say that there's a 300% increase there. This is a breakdown of what systems are on what types of ship. The pictures on the left, I'm not going to go through this because I don't have enough time, but the pictures on the left, 2 of those are Chinese tankers that are already installed. Others are simulations, but all of these are on order. And we actually have, I think the order book for 24, 25 for new builds is already, I think, 11 tankers. That, of course, retrofits are increasingly, how can I say, easier to do as we're moving along the learning curve. So from the announcement of an installation through to the actual installation, that's coming down to months rather than the best part of a year. And indeed, the foundation plate, if you're putting foundations on for, say, a Flettner rotor, it's a couple of weeks of work, but the actual installation, I think the last one that I saw was 5 hours. So a ferry came in, had the installation put on, 5 hours later, she was back out to sea with fully loaded with the rotor in operation. This is just touching on where we are in the development curve. So I think everybody's seen these kind of S curves around innovation. We're pretty much in that area of early adopters, but moving towards more kind of system integration, where we're getting a lot more, how can I say, development, a lot more installations. Feedback from those demonstrator vessels is now helping us to integrate those systems into the ships. Now, this ship, just to give you a quick heads up, this is a ro-ro launched earlier this year with four wing sails. She's delivering the Ariane rocket parts from France over to French Guiana. So she's a new build designer made. Now, we did a survey earlier this year, and this was a fairly open survey, but we requested that IWFA members didn't engage with this. And we had the response on this particular one, 59 stakeholders, 19 of those were ship owners or ship managers. We also had about 25 policymakers on a different part of the survey. But I'm not showing the policymakers because that's almost identical results. Now, all of the fuels, actually, that's pretty much what I've seen on all of the other surveys that I've seen in the market. But what most of the surveys haven't done when we're talking about the energy mix, 2030 and 2050, is wind propulsion wasn't added as a energy source, it was added as an energy efficiency measure. Now, what we're seeing here is when we separate them out between wind assist and primary wind, then wind assist is seen as a significant player in 2030, primary wind not so much at that time, but moving up and becoming more important in 2050. And please remember that the survey respondents could only choose 5 options here. So wind, if we combine the two, actually was very significant because they used up one or two of their choices with wind. Now, of course, they're responding to an IWSA survey, so we take this as indicative rather than definitive. Some people were very anti-wind, others were very pro-wind, and we had, of course, a spread in the middle. Some barriers to uptake, of course, I think this probably reflects some of the results we saw from your survey just at the beginning. The financial issue, ROIs, costs, etc., obviously bottom line issues, but also the operational aspects, import, the intermittency of wind. Indeed, that's being challenged, and we'll hear a lot more about that from the other speakers around wind routing, etc. But also, the crew safety issues as well. Market forecast. So I'm just coming to the last few slides. Just to give you an idea that this is the policy pathway, if you like, and the 3 flags are actually the indicative checkpoints that were passed in MEPC 80, and then the final net zero around 2050 or so. Now, what we're seeing is none of the policy instruments is actually strong enough to decarbonize by itself, but collectively, this is creating a lot of pressure on the industry, as I'm sure you're all aware. So collectively, this is saying we have to go towards zero emissions, and we have to be moving far quicker than we are now. Of course, wind propulsion is a zero emissions source. So whatever else you're deciding, you can use wind. The dotted line going through the middle is a combination of forecasts made, one by the EU in 2017, and then followed up by the UK government in 2019. The EU estimated up to 10,700 installations. Primarily, they were looking at bulkers, tankers, and container ships. We think that's quite conservative because Ro-Ro's general cargo weren't included. The UK government then took that out to 2050 and estimated between 40 to 45% of the global fleet would have some form of wind on board. Finally, just a very quick look at the trends, and it's always a bit of a chicken and egg. The trends develop as we get more wind propulsion systems on ships, but we need the trends to be developing to get more propulsion systems on the ships. Wind routing that I've mentioned already is increasingly sophisticated. So maintaining your ETAs, you can plug into these systems. If you want to maintain your ETA, what is your best route? If you want to maybe reduce your ETA, maybe by 20%, you can get far more substantial amounts of wind power for the ship. Now, these are based on sort of 50, 60 years of meteorological data, increasingly accurate. Optimization, we're looking at things like satellite forecasting, sensors on all of the systems. Even LiDAR is being investigated, which is used on wind turbines. to map out sort of 20 kilometers away from the ship, what is the shape of the wind coming in? So these are ways to optimize, and there's going to be a lot more development there. Scaling production. A number of our members are already moving production over to China. We've got scaling going on in Europe as well. And I think we're over 1,000 units per year capacity across the entire association. But for smaller units, of course, that's easier to build. Larger units are going to take more time. I mentioned wind ready. I think I've mentioned containerized. Actually, there'll be a chem ship. Chem ship will have 2 containerized wind systems installed on one of their ships at the end of this year. Energy harvesting. Now, this picture actually is of the MOL designed Wind Hunter, and this is a ship very heavily wind rigged. She will be operating on trade winds, and she will generate so much energy that you'll have hydro turbines coming out of the hull, and these will generate electricity to be turned into hydrogen and stored in toluene in 1 or 2 of its tanks. So we're starting to actually look at a new paradigm, a potential new paradigm of actually generating not just the fuel you need on the ship, but also a cargo. And that really starts to unlock some interesting business models. And that's all, sorry, that should be, you'll see on the right side, that should be in operation. That one, the full-size one, by 2030, hopefully earlier. But there are a number of other primary wind vessels that are in design. The one on the left, the Neoliner, is already in production in Turkey, and the other 2 are coming online 2025-26. And this is my final slide. So we like to call this a win-win-win situation. All of the companies that are listed on here, and I could have probably introduced another 3 or 4 slides, all of the companies with their logos on here are involved with wind propulsion projects, either installations, testing, certification, or actually some of them are even producing their own systems themselves. So thank you very much.
Thank you, Gavin, for bringing us through a very good introduction on the landscape of how the wind power assistant technologies have evolved and has been applied, I think, and what's to come. I think without further ado, we will have Mr. Frederick Gerhardt of Rise Maritime to bring us through a tanker technology overview. Thanks.
Yes, thanks very much for introducing me. Can you hear me, Casey?
Yes, I can hear you. I think the audience can as well.
Okay, good. Yeah, Gavin mentioned that the number of wind installations will explode over the coming year. So explosions are also the topic of my talk today. This is what I'll try to go into a little bit here. How do I go back on this? And you just click a few views. First trigger happy there. Another one. Another 2 probably. Sorry for this. Yeah, so I work at RISE, the Research Institute of Sweden. We're a big company with about 3,000 employees. And one of the test beds that we actually operate is in Gothenburg. Most of you in the maritime world might know this as SSBA. We now call SSBA Maritime Center, have been around for about 80 years. We have a towing tank, a large model testing basin, a cavitation tunnel. So yeah, model testing facility, but also a maritime consulting company. And since a few years back, we also have a wind propulsion lab. So we've worked a lot on wind powered ships. And now wind power, is that not, well, did we not hear this before, and did we not have it, and did it not end this way, like shown here in the picture? But as Gavin explained, we're talking about modern systems. We're not talking about square riggers and the canvas sails of the Temeraire. We're talking about, well, basically the 7 categories, of which I've taken the 5 more important ones here. The 3 main categories that are sort of have most installations right now are the wing sails, the hard sails, the rotors, and the suction wings. And I thought I'd give you like a 30-second lecture in fluid dynamics because they all work the same way. They are wings producing lift and drag, like there's wings on an aircraft. So they produce lift, that's a good thing. They produce drag in the direction of the wind, which you don't want. If you increase the angle of attack, that is the angle between the direction of the incoming wind and the wing, then you start producing more and more lift until you finally reach something which is called stall. This is where the flow can't follow the shape of the airfoil anymore. It starts to separate, and this is something that you don't want, because after this, your beneficial part will just drop. So the big question is, how can you avoid this? How can you delay the stall as far as possible so that you produce as much beneficial lift as you can? And there are a few techniques around this. Those here is something that's used on every commercial aircraft. If you look out of the window just before landing, you see flaps and slats extended, and they give you a little bit of extra lift. But there are other, like, more advanced techniques. This here it's called boundary layer profile. So you've got a very fat profile in the beginning, and normally the flow would separate somewhere around here because it can't follow the curvature. The boundary layer, that's the innermost layer of fluid, can't, well, cling to the wall anymore. It doesn't follow the contour, and then it separates. But if you just suck off this boundary layer, your streamlines will look nice again, and you get a lot of extra lift. There's other ideas. Instead of sucking off the boundary layer, you could help a little bit by rotating the wall, and you see where this is going. This is basically, there's a sort of physical principle behind those 3 most common systems. Something to mention maybe here that the 2 top systems here, the purple and the moving wall rotor thing, they're active systems, so they require energy to operate. This is something that you need to keep in mind when you do sort of the overall balance of energy on your systems. And now you will probably ask yourself which of these systems is best. The problem is there's no simple answer. It depends on a lot of factors. For example, the routes, how close to the wind do you want to sail, but a lot of other factors. You can all consider them, and then what it finally boils down to is really what system does give you the most bang for the buck, what's the best return on investment there. And talking of the benefits of the systems, the bang they can score in those three areas, really. Like wind propulsion can help you with rules, with EEDI, EXI compliance, with the ETS, CII, IMO regulations. So that's rules, but they can also produce real savings in terms of fuel, money, or CO2. And another area that's becoming increasingly important is consumer expectations. It's kind of an image question. It's really nice to be able to provide green transport. I thought now I talk a little bit more specific about tankers maybe. And the first thing obviously you need to look at is if you talk wind propulsion, is really the availability of wind. This is a map of the world showing the wind speed potential. The blue area sort of around the equator is that's the doldrums, almost no wind there, and then the red bits are the really windy areas. So you've got the roaring 40s down here and so on. And if we talk about tankers, and maybe above all oil tankers, VLCCs, which I'm looking into in a minute, you see a concern. Maybe it's not so much of a problem, but you see that some of the routes, I don't know, Persian Gulf to Singapore, for example, they are in sort of not very good areas, so the wind speed potential is not very high. There's other routes like Gulf of Mexico to China, which actually have a large potential down here. But you need to look at this case by case, and then obviously tankers, VLCCs, they operate on the spot market, which brings a added complexity to those kind of predictions here. This is a case study which I wanted to present to you today. It's a European Union funded Horizon project called Optiwise, where we as RISE work together with Euronav and the sail provider. And we looked at the energy saving potential of installing wing sails on a VLCC. So we sat down together with Euronav, looked at installations, how many wings could we stick onto a VLCC if we take into account interference with deck equipment, all the pipings, cranes, and so on. And in the end, we figured out that we could really stick up to 8 wing sails on a ship like this. So we took this further and looked at energy saving potential and did a few routing studies. And we also looked at how it influences the EEXI. This is already a very effective ship, built in, I think, 2019 it was, with energy saving devices and so on. So it does comply with the EEXI as it is, as a motor ship. If you would stick the 8 wing sails on, you could also comply with EEDI phase 3. So that's really a good saving here. So if this was a new ship and you would equip it with those 8 wings, you would also fulfill the phase 3 requirements. As you all know, like EEXI is a bit of a paper tiger. It's a dead number which ends up in a technical file somewhere and no one looks at it again. A step in the right direction, which actually takes real fuel consumption into account in some way or the other, is the CII. Here you've got CII values or emissions in grams per ton and mile for those routes. And you see that this TD22 route is actually the windiest route, and there's some good energy saving potential there. If you mix those numbers for those route up with together with operational data from real ships, and you sort of recreate last year of operations, then you will find that you can extend your C rating by about 2.5 years or so by installing those wind propulsion devices. Most interesting, like real saving fuel potential on those routes. So for the green route, again, you see between 4 and 6 tons per day fuel savings on the VLCC. So it's quite some potential there. I should say this is operating at 15 knots, so the fuel saving potential goes up a lot if you drop the speed to 12-ish knots or so, but nowadays we're operating at 15 again. So this was the benefits, the bang. The question is what about the buck? At what price do the benefits come? And there's obviously CapEx and OpEx, but there's also other aspects which I just shortly wanted to touch upon. There's technical challenges about installing those systems. Above all, the yaw balance of your ship will change. You see 2 simulations here which we've done where we've placed the device very far forward, and you could keep the course, it's all nice and fine. But if you place the device too far out, you can actually start to turn it to the wind and lose your course keeping ability. So you get eventually locked in irons here. So you either then need to move the device or have a bigger rudder. But this is something that you should look into very early, and it can be done in simulations like this. There's also a whole lot of operational challenges, visibility issues, like in this picture here from a sea trial. The pilots didn't like this because they couldn't see their marks. This is in a channel, and they just couldn't see line marks. Here's a simulation of operations like a tacking maneuver in a confined fairway. So those things can be analyzed before, and also, for example, in a simulator here. And here's a few more pictures. Sorry, can you go back again? Before I hand over to the next speaker, I mentioned site force generation. The sails produce site forces. You somehow need to counterbalance this, above all, on more powerful installations. This is a CFD study or a tank test of a little fin like a dagger board. There's seakeeping aspects. This is interesting. This is a seed file of a real device. So to basically confirm savings in real life. And then the last bit, the picture down the bottom right here, is our methodology to help people like Eric from Woodfield, who will be the next speaker. It's a side-by-side comparison of competing wind propulsion technologies on the same ship. So you've got your baseline tanker here, and you can equip it with Flettner rotors or small or big wing sails. And you can run it along different routes, U-routes, and in the end, you get the fuel savings predicted by the same system. This is what we call a level playing field to compare all the devices. And this is actually what we've used for Utfjell at the beginning of the year. So before they decided to install suction wings on a tanker, they came to us and we ran it through this system, looked at a whole lot of other devices and device placement, number of devices, device sizes, and so on. And in the end, they decided for this configuration. And I think we will hear more from Eric in a minute. With this, thanks very much. And
thank you, Frederick. I think it was that's a very good sharing for helping us to connect the dots on how the technology adoption can translate to the operational needs like route planning, compliance, and fuel savings. Yeah, I think like what you have introduced. Of course, we'd like to thank Eric Hotland of Oshfell for coming forward and to be open in sharing their rationale and thought process on their wind-assisted propulsion systems project and where they have reached and also the journey that they've gone through so far on their project. Without further ado, Eric, thank you. The floor is yours.
Thank you, Casey, and thank you to INTERTANKO for inviting us here today to share some perspectives on the role of wind-assisted propulsion systems, seen from Odfjell's side. But I think we have to look at it in a much more broader perspective. So because this is part of, at least from our point of view, this is part of energy efficiency. And I want to share with the audience here today, or the participants, let's call it the rationale behind why we are walking down this pathway with the wind-assisted propulsion system. And because of that, I think I need to spend a couple of minutes just to recap our perspectives on green fuels, on the decarbonization journey. Look a little bit into the existing energy efficiency toolkit, and then I will put the wind-assisted propulsion system or project into that context before I summarize and conclude. I think several of the participants at this webinar are probably well aware of the quality analysis that Odfjell made a couple of years ago. We have been working on that for many years. Also presented to INTERTANKO earlier, and also presented to the IMO. But as I said, I just want to recapitulate a little bit, because there are obviously fundamental challenges with green fuels. The first of those 5 or 6 fundamental challenges is the renewable electricity demand that shipping will require. I just want to remind all of us that to decarbonize the deep sea segment in shipping alone, it will actually require more than half of the renewable electricity that is available in the world today. And that is a monumental number. We need 5,500 terawatt hours of electricity to produce the green fuels that deep sea requires. And for comparison purposes, entire EU consumes 1,700 terawatt hours. Norway consumes 140 terawatt hours. And we are looking at 5,500 there. So it's a huge number. And I think that is the center of gravity when it comes to decarbonization of deep sea shipping through green fuels. The second challenge is that it's just a sad yet mathematical fact that there is nothing that we have looked into that gives so little greenhouse gas reduction potential per kilowatt hour of renewable electricity input as to produce fuel for aviation and shipping. One of the reasons for this, or the primary reason for that, is about the energy losses in the process. Where you have renewable electricity, 1 kilowatt hour, then you have to produce green hydrogen in order to produce the other alternative fuels, whether that is ammonia or methanol or what it is. And in that process, you lose 30% of the energy. And then when you convert it from hydrogen to methanol or ammonia, green methanol, green ammonia, you lose another 30%. And then you put it on the ship where you lose 40, 50, 60% of the energy in the engine itself. This is the reason why we come so bad out of this. We are looking at an 80% energy loss from renewable electricity until the energy hits the propeller of the ship, to put it that way. The fourth fundamental challenge with green fuels are the carbon leakages. Because if we are to produce green fuels for deep sea shipping, taking 54% of the renewable electricity in the world to do that, then that electricity demand, it has to be replaced. Otherwise, the lights will go off somewhere, right? The question is then, what will it be replaced by? When we know that 61% of the global electricity grid is currently non-renewable, that number is unchanged the last couple of years. And this means that when we create this energy or electricity demand, it will be replaced basically by this grid, meaning that the emissions from shipping, they will actually just go up. But we will not see it because we have transferred it into another sector outside of shipping. But the emission ratio from shipping of all the emissions in the world will go up between 2 to 8 times according to our analysis due to these carbon leakages or replacement emissions. The fifth fundamental challenge with green fuels is about cost premium. If we look at the electricity cost the last 15 years in EU, we see that just to produce green ammonia or green methanol will cost approximately $2,500 to $3,000 per ton for green ammonia or green methanol. And you need 2 tons to compensate for 1 ton VLSFO, meaning that we are looking at a VLSFO corrected price, equivalent price of around $6,000 per ton. So this is basically 10 times as expensive as today's fuel. So to us, this is at least a kind of a reality check when it comes to the green fuels, and it tells us that this is not going to be solved tomorrow. In fact, our position at this stage is that we believe that the best holistic contribution for us as ship owners in the energy transition phase is not to change to green fuels yet, because this is, from our perspective, not a race to zero, it's a marathon to zero. But we have to work on energy efficiency until sufficient renewable electricity is available, because then it will be our turn. It makes sense. Now, of course, we cannot energy efficiency ourselves to zero emission. That is clear. But as I write there, on the road to zero, we can definitely contribute significantly through efficient operation and utilizing available technology while renewable energy infrastructure ramps up, because then we can bend the emission curve, and we can do it now. And by that, we can buy ourselves time. Because if it is one thing we need, that is actually time, unfortunately. Because if you look at the infrastructure required to build these 5,500 terawatt hours of renewable electricity, you get almost flabbergasted out of it. Because our demand, if we are to decarbonize to green fuels, equals 771 nuclear plants, or almost 600,000 onshore wind turbines, 3 megawatt turbines, or 12 billion solar panels. I mean, in the world today, there exist approximately 2 billion solar panels. We need 12 only for shipping, or for deep sea shipping. Or the last alternative that we have looked into at least is approximately 140,000 offshore wind turbines. So the infrastructure here is just enormous. This is not going to be solved within the next couple of years, that is for sure. Add to this picture that there are 2,200 carbon neutral fuel projects announced globally according to DNV. But we also know that less than 5% of those, there has been made an investment decision. Now, it is in this context you have to see the reason why Odfjell is so focused on energy efficiency. Now, most of you have probably seen Odfjell show these kind of technologies and operational improvements earlier. I will not go into detail on that. I just want to bring it forward because I have an important message on this one. The message is that even though this does not say zero, or it does not say 100%, well, they actually work. And I think it's fascinating to attend conferences and follow public debate where we discuss this huge infrastructure developments required. We discuss these multi-billion-dollar technology projects. We talk about hydrogen, ammonia, methanol, and that's fine. We have to discuss those items because ultimately they are the ones to bring us to zero. But what I'm trying to say is that let's not forget that in my hand now I hold something that costs $5 and it can reduce your emissions by 15%. I hope you can see that. And I think that is the main message here. We of course, we have to look into what brings us to zero, but let's not forget those more simple stuff that incrementally help us along the way. And that is exactly what I think we have demonstrated in Odfjell, where we now have reduced or improved the carbon intensity by 53% compared to the average IMO baseline for our 2008 fleet. So it works. And then you can of course say that, yeah, but it is not zero. 50% is not good enough. We are looking for 100. And of course, if you look on energy efficiency and you look vessel by vessel, that is correct. As I also said earlier, that we cannot energy efficiency ourselves to zero. But I want to challenge this statement a little bit. Because if you look at our AER in 2008, and we see that today we have, through energy efficiency, both operational, technical measures, fleet renewal, we have achieved this AER. What if we had not done anything on energy efficiency, but instead we had just phased in a number of new ships with zero emission capability so that the fleet AER had ended up at the same level as we have done today? What would that mean? And it was quite surprising for us to see when we did this very simple calculation that what we have done on energy efficiency actually gives the same result as 21 zero-emission vessels would have done. And that is the reason why I say that I want to challenge the notion that energy efficiency cannot bring it to zero. Because 21 out of 53 vessels, zero-emission equivalent in terms of energy efficiency, that is quite a decent number. And it just tells us what we as a sector can achieve by utilizing existing technology and do something meaningful with regards to emission reductions today, instead of just, talking about the future and the fuels somewhere down the line that will solve everything for us. I think it's at least for us, a wake-up call. And I think this is exactly what DNV also has now brought to the table in the latest maritime forecast, where you can see that they say that in order to achieve what we need to achieve by 2050, almost 40% of that must be done through energy efficiency, through a reduced energy demand. But I think also it's important to have a look at what they say about 2030, because if you follow the debate today, and this race to zero mentality, we are talking about something that shall bring us to zero by 2030. And I don't think that is realistic at all. And you can see it also here from DNV that they predict that 64% of our goals by 2030 needs to be taken through energy efficiency. Of course, when we talk about energy efficiency and you know, at least everything we have done in Odfjell, we have installed more than 130 different, more than 130 project installations. The toolkit is actually starting to run empty. So we need to scale this up now. And the first thing that we have been doing now of these technologies that we call novel technologies is the air lubrication project, which we have recently installed on one of our ships just a couple of weeks ago. Here are some pictures of the installation. So the idea here is that we have installed 3 air release bands on the flat bottom of the ship. We have a couple of compressors producing air, and we release 80 million air bubbles under the flat bottom every minute, creating a cushion, air cushion that the ship will sail through. The idea here is, of course, to reduce the friction or the resistance through water. So that was installed a couple of weeks ago, and we are now shortly starting the trials across the Pacific, and that would be a very interesting trial, to put it mildly. We expect a minimum 7% net saving of this, but it could also go higher. We are also into this solid oxide fuel cell project. This will be the world's first fuel flexible, zero emission capable solid oxide fuel cell, with the potential of reducing the consumption by 50% compared to a combustion engine. This is also, of course, very interesting for us. This is a project that we have been involved in for the last 5 years, and we plan to install this and test it in December next year. On the same vessel, we also plan to put the suction sails. So here, the plan is to retrofit 4 sails on one of our Hudong class vessels. This is a 40,000 tonner. The sails are 22 meters tall, 4.5 meters in diameter. They weigh 35 tons each. And because of the height, which we have decided to cap on the same height as basically the vessel itself, so we don't need to worry about have to lower them down or something like that, because that adds a lot of complexity and costs, of course. So that is the reason why we have them at 22 meters. The technology here, I'm not sure if you can see on top here, you can see these 2 items here that are 2 fans. They suck air through holes vertically down on the sail. And as they do that, they create this over under pressure situation that gives a net positive lift for the vessels. The potential here from our perspective is pretty big. What we have as an expectation, as an average expectation here, is around 10% every day at sea in a worldwide trade. But I think that number is in many ways irrelevant, because that is how we normally look into a energy saving device technology, is that you get the saving and then you get it every day. This is not the case for sails. Of course, on some voyages we will have 0. On other voyages we will have significant saving, that is for sure. So this average number is not that interesting, at least from my perspective. Now, what's good about this suction sail technology is that it has a very high lifting coefficient, first and foremost. Second is that it is fully autonomous. The third argument for this kind of technology is that if you are in an area where you do not wish the sail effects, it could be an area with dense traffic, or it could be a very rough weather or whatever, then you just push a button to stop the fans, and by that you also stop the entire sail effect. Then it will just create a drag on the same way as all other structures on the vessel will create a drag. So I think this is a very nice technology, at least for our vessels and our trade. Here you can see how it works, where the wind comes in and hit the sails. On the aft side here, you see that we have this stalling that was mentioned by our previous speaker, basically just creating a drag. When we start the fans, then you get this over and under pressure situation, and you get a rather significant lift from the sails. Now, let's put this into context with the Fuel EU Maritime regulation that will start January 1st, 2025. This is really interesting. Because as probably all of you know, we need to improve the greenhouse gas intensity in the energy used by the ships from 91.2 to 89.3 from 2025 to 2030, so 2% down. Now, if the relationship between the force from your sails, the relationship between that and the power from the engines is more than 0.15, then you get a reward factor here that you put into the Fuel EU Maritime energy balance equation, which you can see here is quite nasty. You get a coefficient here, so that is for 5%. Now that doesn't sound much, but if you look at this, when we calculate the energy balance of this class of vessels, we see that in 2025, they will have a deficit of 126 ton CO2 equivalents that we normally would have to offset through biofuel or any other fuel for that matter with lower GHG intensity. But when we install these sails, we calculate that we will not get a deficit of 126 ton CO2 equivalents, but we will actually get a surplus of 197, meaning that in a Fuel EU Maritime context, the sails will not only solve the issue for this ship until 2030, but it will also solve a similar issue for two and maybe more sister ships as well, because you can pool the compliance across a fleet or a pool of vessels. So this is very interesting, because that means that if you equip, let's say, 10 ships with this kind of technology, then they solve the Fuel EU Maritime for 20 to 30 ships without the requirement without putting stress on the renewable electricity situation that I described on a previous slide. From 2030 onwards up to 2035, this will of course help you a lot on the way. It will not solve it as it is today, but it will help a lot. I will get back to that on a later slide. So just to summarize this, shipping does not have its own atmosphere, and I think it's important to continue to remind ourselves that what we do at scale, that can have consequences outside of our own sector. And this is why we have been so vocal on this silo thinking item. To decarbonize one sector, that can transfer the emissions to another sector, and it can also increase the net global emissions until sufficient renewable electricity is available. This is the reason why we do not wish to push a shift to green fuels now, because we believe that the renewable electricity infrastructure is not ready for that. And that is the reason why we are so rigorously focused on energy efficiency, because that works, and at least it can bend the curve, and it can provide tangible emission reductions from day one through on the shelf and rather cheap, business sound installations. But I think it's important to also emphasize that when you look at it on a fleet level, remember now that the energy efficiency that we have done in Odfjell gives the same environmental effect as 21 zero-emission ships. And as I mentioned, to us at least, this was a wake-up call. And again, it was achieved or has been achieved through existing technology and without stress on renewable electricity. But it has also reduced our costs and it has increased our competitiveness. So this is a very good proposition. What I think is, or at least puzzle us a little bit, is that according to Clarkson, 75% of the world fleet has not installed any energy saving devices yet. Therefore, we believe that the reduction potential there is actually huge from shipping, that we can quickly bend the curve, which is exactly what DNV points out in their maritime forecast for 2023, why that is so important. And I think it is in this context that the SAIL project, the Wind Assisted Propulsion System project in Odfjell, has to be understood. Just to conclude on energy efficiency is that it answers to all known greenhouse gas regulations, and WAPS, or Wind Assisted Propulsion System, is one of the very few energy efficiency toolkits or tools that can offer 2-digit reduction measures. If we look at the EEXI, for instance, which regulates the energy efficiency of the ship, well, you can improve your EEDI and EEXI by 15% through wind-assisted propulsion systems. It can improve your CII rating. It will reduce the number of CO2 quotas that you need to purchase within the EU ETS. It will also reduce the volume requirement of alternative fuels for fuel EU maritime compliance. And it will also reduce the alternative fuel volume requirement within the IMO GFS when that starts to happen. So I think this slide just concludes the beauty of energy efficiency and the wind-assisted propulsion system concept, because it ticks off basically all the boxes from our point of view. And by that, I think that concludes my presentation, and I say thank you for the attention.
Thank you, Eric. And yes, I think that was very insightful, especially on the rationale and the thought processes, given that this is a long marathon in terms of the decarb journey. I think, may I also say that Odfjell is also one of the pioneer companies who started fleet performance monitoring with sensors installed throughout to monitor the effects of the different improvements that are made. Yeah, so thank you for that, Eric. Yeah. With that, in fact, we actually would have Mr. Chen from AMCL to present on the experience next, but due to some rescheduling, we will have Mr. Simon Schofield present first on from BAR Technologies, presenting first on the takeaways for installing the wind assisted propulsion. So Mr. Simon Schofield, please. Thank you.
Thank you very much. Just share my screen with all. Okay, can everyone see the slides? Can you see the slides?
Yes, we can, and we hear you well. Thanks, Simon.
Great, thank you. So my name's Simon Schofield, and I'm the CTO of BAR Technologies. And for those of you that don't know who we are, we started life as an America's Cup team, so designing yachts for kind of very high-end racing, which is obviously the ultimate wind propulsion sport, if you like. And in 2017, at the end of an America's Cup cycle, we formed the technology business, very similar to the way that a Formula One team would have an applied technology company, to take the tools and learnings and kind of the engineering talent of those competitive race teams and apply it to the wider marine industry. And we developed a product called Wind Wings. Now, wind wings is a large rigid 3-element sail. So Gavin earlier on was talking about different sorts of technology. So this is what he called a rigid sail or a rigid wing. But what's unique about ours is it comprises of 3 elements. So it has a leading element, a main element, and a trailing edge element. And they work very much like an aeroplane wing when you're coming into land and you have a multi-element wing to maximize the amount of thrust you're producing. But it also allows you to produce a very flexible tool that can be used over a wide range of apparent wind angles and apparent wind speeds. Obviously, and other speakers have touched on this, when it comes to developing your fuel savings, it's a very complex problem because it depends on the conditions you're sailing in. But what we do is we do a lot of simulations based on historic weather data. And if we look at a ship operating globally all around the world, we'd say through the life of that ship, each wing will deliver savings on average of 1.5 tons of fuel a day. But we'll come and see what the savings are in service shortly. The wings are fully adjustable, both in camber and angle of attack, and they fold onto the deck. So when we're undertaking pilotages, port operations, or in adverse conditions, they can be folded onto the deck. And there's a couple of configurations available, kind of with vertical rams or horizontal rams, depending on the vessel you're fitting them to. They're robust in their construction. They're designed for 25 years. Then they're approved by DNV, and they consist of a steel primary structural member and then composite fairings or aerodynamic components, which are constructed in a very similar way to a wind turbine would be constructed, an offshore wind turbine blade. And in fact, they're manufactured in the same sort of facilities. So there's a couple of exciting installations which we've launched recently. The first is 2 wings on a Kamsarmax called Pyxis Ocean, which belongs to Mitsubishi Shipping and is chartered to Cargill. And the second being a larger Newcastle Max, which is owned by Berger Bulk. So since we've launched these wings, especially on the Pyxis Ocean, we've been spending a lot of time gathering data, understanding the performance. In fact, we've had some of our staff doing long ocean voyages on the vessel as well to really undertake in-service testing. And I was just going to share a brief example of some of the data points we've recorded during some of the first voyages. So during one of these first voyages, which was from Singapore to Brazil, we undertook a number of tests. And one of the obvious tests we can undertake on this wing is to do speed runs with the wing up and then fold them down, do runs with the wings down. And obviously that provides us with true back-to-back testing, assuming the wind conditions stay constant, which generally they do at sea in the time periods we're looking at. So what we do in these graphs, we've got segments where they're green, where the wings are up and operational, and then we've got the yellow segments where they're being folded, and then we let the vessel speed settle. I think the reality is we probably didn't wait long enough, and we can look at the differences in performance with and without the wings. So first thing that's obvious, if we keep engine RPM the same, and we put the wings up and then we put the wings down, we're seeing about a 2-knot delta in vessel speed. Associated with that 2-knot delta in vessel speed, you can see that the engine power increases as well. So not only are we decreasing speed, when we drop the wings, we are increasing the engine loading. We can then take that data and use that to check our models. And then from the models, we can verify via strain gauges the amount of thrust we're producing on the vessel. And we can effectively run back-to-back comparisons with and without wings which allows us to do statistical analysis along a route. And here's some examples again of some savings, where along this segment of time, it was over several days, but the wind was generally between 18 and 25 knots of wind. So not massively strong winds, but not light winds. The wings are designed to operate in up to 40 knots with 50-knot gusts. So this is kind of middle of the range, if you like, and is actually quite typical of a lot of the conditions we see the vessels operating in. The wind directions were good here. They were favorable. So, you know, as I say, the savings are dependent on the wind direction and wind speed, and we shouldn't kid ourselves. These are good wind directions, but you can see the savings in power are huge. We're seeing from 2 wings alone in kind of 23 to 24 knots of wind at 80 degrees true, so slightly forwards of the beam, savings of 36.6%. And that equates to a reduction of about 2,500 kilowatts of power. When we extract some longer segments, and there's a few examples here. There's a 24-hour segment here when each wing was saving 5.6 tons of fuel a day. So on that vessel, each of the vessel was saving over 11 tons of fuel per day. And you can see that although the wind speeds are changing slightly and the wind directions are definitely changing due to the flexibility of the 3 elements and the way the wing is automated and configured, our fuel savings are very high. So I said at the start that we look at a global average of 1.5 tons a day. Obviously, if you're operating on a route where there's good wind conditions, the savings are an order of magnitude better than that. And it's important that when we're looking at wind technology, we look at the routes we're operating on and take that into account. What is really, really promising is that the correlation between the predicted fuel savings and the actual fuel savings we're recording and we're looking at through the back-to-back testing are very, very well aligned. If anything, our predictions are slightly conservative, but this gives us good confidence that when we're looking at a new vessel or a retrofit and we're looking at specific routes, we should be able to very accurately simulate the amount of fuel we're going to save statistically, and also the payback periods and the business cases. So a few images of the wings in operation. Obviously, it's important that they don't impact on the operations of the ship as much as possible. So on the left, we see the wings are folded down onto the deck. Obviously, that has some advantages during operations in kind of restricted areas where you want more visibility through pilotage, and of course in bad weather. And this vessel just came through the Bay of Biscay in some very, very bad weather, and we've got footage of waves breaking over the wings in these conditions, and they survived very, very well. But you might get into adverse conditions where you don't want the wings producing lift, but you don't want to fold them either. Maybe it's a short period of time. And the central image there is them in what we call the active feather mode. And the advantage of this is they're aligned to the wind. The wings have no camber left in them. So they're producing very, very little drag. So although they're upright, their effect on the performance in these adverse conditions where they're not producing lift is very minimal. And then finally, it's an image of operations of loading and unloading, and it's been very well received by the ports. It's proving to be very unintrusive. Obviously, the port operations are much more complex for a bulk carrier than they are for a tanker, where the installation can be kept away from the manifolds, and it kind of doesn't really affect the port operations at all, especially while they're folded down. So next for us, firstly, we have got this ongoing data validation. We will be making that public, but first of all, it's being verified by a third party. You know, we don't want everyone to believe us. We want everyone to believe a a third party that's verifying that data, and we'll be making it very, very public and publishing that shortly. Secondly, we're scaling up production, and I think Gavin mentioned that a lot of us are scaling up production in China, and that's exactly what we're doing with the capacity to build hundreds of wings, and then also some other production facilities in other locations around the world. And we've got a big drive for both new builds and retrofits, and probably for this audience, one of the most interesting projects we've got going is two LR2 new build runs underway. So 2 yards fitting 3 wings to LR2 tankers. Thank you.
Thank you, Simon. I think for bringing us in depth into one of the key solution, wings. I think the next coming on next speaker, Mr. Chen from AMCL under the China Merchant Energy Group will bring us through some real life experience of the technology being adopted and used on board. I think it's been almost a year since the new Aden, the VLCC fitted with wing sails, has been in the water. May I invite Mr. Chen to take the floor, please.
Okay. Thank you, Casey. Good morning, everyone. Today, I will share with you our company's application of wind propulsion. Its technology benefit both commercial shipping and decarbonization. As you can see, this shipping industry is increasingly favoring wind propulsion due to the urgent need to reduce carbon emissions and mitigate man-made climate change. Once again, the shipping industry is turning to wind propulsion, which has a wide range of applications in modern commercial shipping. From wind assisted models vessels, where the wind provides auxiliary propulsion, is to primarily wind ships, where the wind service is the main source of propulsion. However, most of these wind propulsion devices are still under the development, testing, or in experimental phase. Currently, only aerofoil sails and flatter rotors are commercially available. As Stephen King, the Colorado Kid, once said, sooner or later, everything old is new again. Modern wind propulsion systems, such as aerofoils, different from the traditional jagging sails, similar to an airplane. The squelette lies in the pressure difference due to the camber of the aerofoil surface. The leeward side always has a higher velocity than the windward side. Based on the Bernoulli effect, this high-speed flow results in reduced pressure in suction compared to windward. The components of lift and drag in the direction of travel help propel the ship forward. The aerofoil shell concern applies a steel support mast, an aerofoil surface, and steel foundation. Mechanical components include aerofoil surface, steel mast, steel foundation, slewing mechanism, and reefing mechanism. Both the mast and aerofoil surface consist of multi-section nested structures. The slewing mechanism consists of a slewing base, slewing support, driving model, and pinion. The reefing mechanism is composed of a hydraulic cylinder and fixed pulley block. The operating principle involves fixing the aerofoil surface on the mast supported by the foundation. Lifting and reefing operations are driven by hydraulic cylinders and fixed pulley blocks to move the aerofoil surface up and down. Rotating operation of both the mast and aerofoil surface are directly driven by driving models and slewing supports within the foundation. Introduction of the aerofoil shells. The aerofoil surface is made of steel. CFRP material. Its dimension include a raised height of 35.6 meter and a self-shelving height of 14.18 meter, with a maximum width of 14.8 meter and a minimum width of 14.4 meter. The operation speed includes lifting speed 1 journey per 6 minutes and reefing speed 1 journey per 6 minutes, while the rotating speed is set at 1 knot per 3 minutes. The drives for lifting and reefing operations are powered by hydraulic cylinders and pulley blocks, while the rotating operation is driven by electrical hydraulic motors using the deck machine hydraulic unit as the power source. The support structure consists of a mass made from snacks, polygon steel structure and a foundation made from cylindrical steel structure. Ambient conditions include available wind conditions up to Beaufort Scale A, survival conditions based on a North Atlantic environmental, low at a probability level of once in every 25 years, less than 55 meters per second. Operation relative wind angle range between 20 degrees to 340 degrees. Operational relative wind speed range between 0 to 25 meters per second, with a maximum thrust capacity of 503 kN. Let's talk about the control system. Automatic. They automatically lift and reef rotates to maximum wind propulsion contribution. Energy saving can be achieved without raising the shell's onboard performance evaluation system, processed with the logical data and onboard main engine data as inputs for calculations, provides real-time evaluation and feedback on wind propulsion energy efficiency, theory, specific fuel saving, etc. Monitor system for lifting and reefing, displaying real-time value of oil temperature, P pipe pressure and T pipe pressure. Monitor system for rotation, displaying the status of inverter, motor, lifting encoder, and rotary encoder. Monitor system for power self-checking, displaying the power status of each device. The green line indicates normal operations, while the red line indicates a fault. Monitor system for communication, displaying the communication status of each device. The green line indicates normal operations, while the red line indicates a fault. The installation of aerofoil cells will impact the following aspects. 1. The seat stability. The cargo of gravity of the vessel will be raised since the cells will be locked on the deck, resulting in an increase in wind induction healing moment due to aerodynamics. Radar visibility. The full raised height of the cells will exceed that of the radar mast. 3. The navigation and collision prevention equipment arrangement. The visibility of navigation signal lights may be affected by fully raised sails. 4. The anchoring, mooring, and towing equipment. There will be an increased project area which may require more equipment and affect the design of anchoring, mooring, or towing equipment. 5. The firefighting system. The blockage caused by shells may create a blind sector that cannot be reached by that firefighting system. Number 6 is vessel's maneuverability. Based on the previous installation, there is no notable impact on vessel handling. The retractable function and control system allow minimize force generated by shells during severe weather. The following interface should be integrated with the visual system. One, the longitudinal stance. The installation of cells will change the weight distribution, which in turn will affect the hull structure. Two, back reinforcement. Additional loads on the vessel structure may require reinforcement to adjacent structures. Three, arrangement for HPU provide the power for lifting and reefing. Hydraulic lines in hydraulic oil tank is about 4 cubic meters. For power capacity, the power demand for lifting, reefing, and rotation is approximately 75 kilowatt. 5. Additional anemometer. Checking wind speed and direction data provide the original anemometer. Determine the optimal rotation angle and ensure structural safety. 6. Signal required by control system. The control system collects multi-signals, such as wind direction. The control system collects and multiple signals, such as Y direction, Y speed, draft speed, and main engine power, shaft power, and oil consumption, etc. 7. Arrangement for cell console. The cell console needs to be installed in both navigation bridge and cell local position. New Vitality is the world's first aerofoil cell VLCC with one pair of aerofoil cells installed. These cells automatically lift, reef, and rotate to maximize Y-assisted propulsion contribution, resulting in a 3% contribution to attain EEDI. Fully load with a service speed of 12 knots and power scale 5, there is a minimum of 5% power saving for the main engine. In the case of wind Y, one of the most favorable wind direction, there power saving of up to 16% and daily fuel saving of 5 tons. When fully loaded with a service speed of 12 knots and power scale 8, under the best wind direction, the power saving can reach up to 45%, resulting in a daily fuel saving of 90 tons. New Eden is the second generation aerofoil cells VLCC with 2 pairs of aerofoil cells and carbon fiber reinforced plastic cell surface, as well as a smarter control system. More independent control scheme, and each aerofoil cells unit has an independent power source. And onboard performance evaluation system and use interface are included. Real-time feedback is provided when energy saving and operation features. Automation seeking is performed at a reefing position, and energy saving can achieved without raising the cell, and 6.2% contribution to attain the EEDI. Now we further discuss the factors affecting cell propulsion ability. Wind resource on a typical route that determine whether it is suitable to install cell propulsion equipment. These wind resources are obtained through statistical analysis of data recorded by authoritative meteorological units over the past few years. The efficiency of propulsion depends on the wind resource along the entire route, rather than at a certain moment. Additionally, factors such as aerodynamic performance, number of installation, total area, and height of a wind propulsion system also influence its effectiveness. To calculate fuel consumption saving accurately, it's necessary to calculate the power provided by cell, compare it with the engine power at speed, and then determine the amount saved. Structural reinforcement is required according to the common structural rules and class requirements, as specified in VLCC. Their longitudinal turns are reinforced with girder and brackets are at the transition position. Impact on stability. For large ships such as VLCC, there is significant redundancy in stability, and the installation of the cell propulsion system has a little impact on stability. For small ships, stability can be improved by increasing the ballast water. Impact on integration with navigation system and visibility. At present, the control system of the cell propulsion is not integrated with a navigation system. For large ships such as VLCC, blind spot for visibility can be avoided through reasonable layout. However, for small ships, blind spots for visibility should be spent by flag state. Radar blind spots can be solved by adding radar or with CCTV. Now, what new operation complexities could arise from the introduction of a new fitting? As an intelligent control system, the cell propulsion system does not require human intervention during normal operation. Human intervention is only necessary in emergency situation to control the cell propulsion. Prior to delivering the cell propulsion system, comprehensive training will be conducted for the crew on principles, controls, and alarms. For maintenance strategies are necessary to ensure reliability and performance. Being a system propulsion system requires regular maintenance for optimal performance. Therefore, the maintenance instruction for cell propulsion will be provided, including maintenance items and cycles for each subsystem. The operation manual also specifies certain required for same maintenance, such as pre and post-use check. Okay, the morning technical sharing on wind propulsion has come to an end. Thank you for your valuable time. If you have any questions, please don't hesitate to reach out to me via email after the meeting. I will be more than happy to help. Thank you again.
Thank you, Mr. Cheng. Yes, I think very insightful, especially I think this is a very so-called from real life experience, especially new vitality. The first VLCC that AMCL or China Merchant Energy has put on water is since 2018. Yeah. So thanks for sharing on that. Okay. May I invite you, Mr. Chen, to just stop sharing the screen? Yeah. Yeah. So with that, actually, we have come to the end of the webinar. We have some questions posted on Slido, but due to the we're running out of time. Maybe we can have maybe one or two short questions. Given that I think there's quite a bit of interest on the real life users experience and users thought process. So I think one of the question I think maybe could be addressed by Mr. Chen. I think in terms of maintenance, right? You mentioned about it, but given that I think it looks like to have automated rotating sails, there's quite a bit of moving parts. Can you share a little bit of an insight of the cost and the effort involved to maintain? I mean, how regular do we need to change parts? on this wind sales. Thank you.
Sorry, I cannot open.
The camera, but it's okay if you can just respond to the question. Do you need me to repeat the question? It's about maintenance. What is generally involved for the sale? Mr. Chen?
Yes, regarding the general maintenance, we just so at this coming 1 year later, not so much the maintenance, only the routing, the checking the hydraulic system, and then checking the valve operation condition. But actually, this is after 1 year running is always normal. So not so much the maintenance job in the routing.
Okay, thank you for that, Mr. Chen. If Eric is still around, I think could be one question that's of interest. I think you mentioned about energy transmission leakages. I think with wind, especially with suction sail, there's also a lot of rotating parts. Do you think all those possible losses would actually matter for your roadmap in terms of achieving your goals? Thanks.
I think that is, if I understand the question correctly, I think that answers exactly to those challenges that I mentioned earlier. This must be seen as short-traveled wind. That is the expression I use, because at least here you don't have those kind of energy losses. You get a direct thrust forward for the vessel, compared to having wind turbines onshore or offshore and then produce the green fuels. You have this 80% losses. If you put the energy source on the ship itself, the wind energy source itself, you have basically zero losses.
Okay, thank you, Eric. Okay, I think given that we have heard from the end users, maybe Gavin from IWSA and also Frederick, if you would like to add any comments to those questions on maintenance and energy losses. Yeah.
Okay. Yes, from the projects, the overview around the maintenance issue, also things like training and safety aspects. Everything that I'm seeing reporting is that they're fairly minimal. They're very much standard maintenance issues. So nothing really with an added burden for crew members. The training, yes, there is obviously some training aspects that would be good for crew members to have. But again, it's a highly automated system. So it's just understanding the maintenance schedules and understanding the emergency procedures as well. On the energy loss, obviously passive systems have a very low energy input just for movement of the systems, whereas obviously the Flettner rotors or rotor sails and the suction wing devices, but those the ratio would be under 10%. So you're getting 90% power out of it with a less than 10% input of power.
I muted myself, sorry. So thank you, Gavin, on that. Frederick, if you would like to maybe add on to what have been said.
Yeah, maybe on the energy efficiency question, like I totally agree with Gavin. Like the energy consumption is peanuts compared to what you get out of those systems. So there's a very small effect that you can forget it. And Eric's point there with green fuels, e-fuels, I couldn't agree more. I mean, in our own analysis, you lose 90% of the primary energy on the sort of conversion chain, not 80, but this is the only difference I think we have there. it's really the combination of energy efficiency measures, operational measures, wind propulsion, which will bring down your fuel consumption to a point where you can actually afford to use those scarce and very expensive fuels. So if you do a little bit of speed dropping, slow steaming, then other operational measures like maybe routing, wind propulsion, then you've already come a long way, and you can afford to buy those fuels maybe eventually.
Could I just add one more point as well on a lot of these measures? We're taking a snapshot of wind propulsion as it is today, but we're on a pathway of quite a steep learning curve as well. So every installation we are learning how to do the installations quicker, the maintenance schedules, everything that we are learning is being folded back. And I think Simon mentioned this, that feedback loop is only increasing. We're seeing the costs of production and the costs of installation also coming down as well. So that's only going to accelerate over the next couple of years, and we'll see some quite big gains in those areas as well. So it's not quite watch this space, but any issues that you're looking at today and costs you're looking at today, within 18 months, 2 years, those are likely to be reduced 30–40%. So we're in quite a substantial learning curve initiated already. Thank you.
Thank you, Gavin. Thank you, Frederick. Maybe just one last question to Eric. I think you have shared with us your plans for the upcoming suction sail project. What do you foresee will be the next step? Is it going to be, we're going to be seeing the whole Oshfell fleet be retrofitted with this? Thanks.
Thank you for the excellent question. Of course, this is a pilot project for us, so any further decisions is based on what we learn from the pilot, and if we get the results that we predict or that we have calculated that we should get. Should this prove to be as successful as we hope, of course, we will continue to install on other vessels as well. But to what extent is too early to say. But basically, this concept, it ticks off all the boxes for our decarbonization strategy. So let's see how it plays out after we have installed it and tested it.
Thank you, Eric. Thanks for that. And also thanks to you, Eric, and Mr. Chen, and to all the speakers for the very frank and open sharing. Yeah, I think it's quite valuable for many of us, especially those in the audience. I think the conversation on this will not end here. I think do feel free to direct any questions or comments or discussions or start anything conversations on this. Feel free to contact us at INTERTANKO if you have problems contacting the speakers. Yeah. So I think with that, I think we can call the webinar to an end today. Yeah. I hope it has been very fruitful session for everyone. Yep. With that, thank you very much to all. Yep. And wishing everyone a good weekend.